Yeah.
Уважаемые коллеги, я рад приветствовать вас снова или первый раз тех, кто не был на вчерашней лекции. Еще раз хочу представить профессора Джереми Вольфа, который сегодня будет делать новый доклад, читать новую лекцию про то, как зрительный поиск, о котором я рассказывал много вчера, взаимодействует с долговременной памятью. Вот я буду переводить в любом случае, потому что сегодня такой немножко, возможно, более сложный, хитрый материал. So, dear colleagues, I would like to introduce you Jeremy Wolfe again, especially for those who was absent yesterday. Jeremy's today lecture is about hybrid search, so it is when you search both in the external space and in your memory. And so let's start.
Okay, thank you. So thank you. This picture is here to illustrate the basic topic that I will talk about today, which is seafood buffets. Suppose you're out to lunch with your mother, and your mother says, go to the buffet and get me some shrimp and a banana and an orange. To do that, what you need to do is you need to have a set of items held in your memory, and you need to have and then you need to take that set and apply it to the visual world. So you need to be coordinating between a visual search and a memory search at the same time. And we were interested in how do you do that? To pick up on a question from yesterday, this is like what happens if you are a radiologist and you are told there's something wrong with Igor. Find out what it is. You have a list of things in your memory of things that might be wrong with Igor, and then you have to search through the complicated image that you have made of Igor and coordinate, again, this memories list and this visual list, and that's what we want to do. So this is my lab in 2012. This, I think, is 2013, maybe. Oh, no, this is 2014, maybe. I showed you yesterday, 2013, with the ice cream. Nice group of people. They keep leaving. But, so here's this basic problem. Find me a bunch of things that I'm holding, and you have to find things that you are holding in memory, and find this in a visual display with lots of items in it. This is not a new question, at least not an entirely new question. Rich Schifrin and his colleagues back in the 1970s, 1980s named this hybrid search. Back in the 70s and 80s, like a lot of research in this field, it was being done with small numbers of letters and numbers as the stimuli. So very reduced stimulus set. So you might be having 2, 4 items in your memory and in your visual display and a few items in your memory set. And the result from the old data was that the search through the visual set was roughly linear as a function of the visual set size. So each item you added to the visual set size increased the amount of time it took to find what you were looking for. And same for the memory set size. The main argument was that this was linear. And so if you're doing the hybrid search, which is the visual times the memory search, then it was basically going to be a multiplication of these two. These both go at a rate of about 20 to 50 milliseconds for each item, and that produces a problem. Sometimes we call this the Facebook problem. Imagine that you have 1,000 friends on Facebook. I know there's Facebook here because since I was in St. Petersburg, people keep friending me. So, which is nice. Anyway, so you've got 1,000 friends on Facebook, and somebody posts a picture of a party. And you want to know, were any of your 1,000 friends in this party of 100 people? This is actually a very famous party. It's the one time that Sigmund Freud, who I think this is Freud, visited the United States. So this is Freud, Jung is here somewhere, and most of the rest are the top psychologists from about 1909, does it say on here? Yeah, 1909 in the United States. Very important psych meeting. I don't know that, I think probably there were no Russians there because the only foreign people there were Freud. That's why everybody else came. All right, so 1,000 friends, 100 people in the image. If it was really linear in both of these, if you start multiplying 1,000 by 100, the numbers get big fast. And it would take you, you can estimate, 40 to 50 minutes to do that task. Even though you're doing, one face every 20 milliseconds. That can't be correct, right? You know that if you're looking at a picture like that, you get the answer more quickly. And we wanted to understand how you get that answer.
Thanks. Так, Джереми сегодня рассказывает про гибридный поиск. Это термин, который в свое время предложил Ричард Шифрин для обозначения ситуации, когда вы ищете одновременно и в зрительном пространстве, и в своей памяти. И, допустим, да, вы идете в магазин, вам нужно держать в памяти целый список товаров, которые вы хотите купить, и одновременно осуществлять зрительный поиск, потому что эти товары лежат на полках. Аналогичный пример можно привести с теми же радиологами, которые на снимках ищут не одну проблему, а целый список проблем, да, которые, в принципе, там можно найти. Вот все это называется гибридным поиском, и классические исследования 60-х годов в области кратковременной памяти, когда испытуемые запоминали короткие списки слов или цифр, показывают, что, в общем-то, по всей видимости, поиск в памяти – это линейная функция от количества элементов, так же, как и в зрительном поиске. И, соответственно, обе функции получаются линейные, но если вы представите такую ситуацию, когда вам, допустим, у вас есть 1000 друзей на Фейсбуке, и вдруг вы получили фотографию, да, на которой сотни человек, и вы хотите узнать вот на этом мероприятии, кто был из ваших друзей, то ваш поиск среди сотни человек и среди 1000 друзей, которые хранятся у вас в памяти, будет, если все это будет абсолютно линейным, он, вообще говоря, будет очень долгим и может занять 40-50 минут, что, в общем-то, не соответствует действительности.
So, what we will do is, we'll take advantage of the fact that you're really, really good at getting objects, pictures of objects into memory. I won't do a classic picture memory demo here, but I could show you, for instance, 100 pictures, each of them for 3 seconds, let us say. No rehearsal, no repetition, just every picture, one after the other. And then I show you 200 pictures. Is it a new picture or is it an old picture? You're going to be, for an experiment like that, probably 90% correct, at least. It's terribly easy to do this. That's another interesting topic, why that is so. But, and 100 is not the limit. The great experiment from the 1970s was done by Standing. He did 10,000 pictures. Takes a long time. And Ode Oliva's lab at MIT routinely does 1,000 or 2,000 pictures in their experiments. It's easy to get lots of pictures into memory. So unlike the old letter and number work, we don't have to limit our our memory set to a small number. We can go to much bigger numbers. And that gives us really a bigger hammer to beat this problem with. So what I'm going to do for this first experiment is I will get subjects to memorize 1, 2, 4, 8, or 16 items. And then I will show them visual displays with 1, 2, 4, 8, or 16 items on there. And I'll measure how long it takes them to find whether there's a target present. So, memorize those. You've already done it. Whoops. Oh, we'll train them to make sure they're 95% accurate on that. But, okay, these are the ones you're trying to memorize. What you want to do in the next, we'll do the clapping again. Clap if you see one of these in the next display. Ready? It's very quiet. Good. It's not there. Okay, let's do it again. Let's do it again. So, this is not like the demos yesterday where you were clapping because, woo, maybe I think he's got a yes this time. You know exactly which item it was, right? What's the item? Yeah, that one. Right. Very easy to do. And it's not hard. I could have done a larger set size. It's not hard to do with a larger set size. Let's look at the data. We'll look at it two different ways. First, I'm going to plot reaction time in milliseconds as a function of the visual set size, the number of items on the screen. And it's going to look like this. Each of the different functions is for a different memory set size. As you go to bigger memory set sizes, it gets more difficult, it gets slower. That's not a big surprise. And the functions are very linear, just like the old data with letters and numbers. Now, let's take exactly the same data points, and we'll replot them now as a function of the memory set size. When we replot as a function of the memory set size, the data look like this. So clearly not linear, clearly curvilinear. Is that interesting? Oh, Igor says. Yeah, good.
Okay. В отличие от тех старых экспериментов с кратковременной памятью на цифры и слова, в исследованиях Джереми используются стимулы картинки. На них, как было показано в свое время, память гораздо лучше. Мы можем запоминать сотни и тысячи до десятка тысяч, да, как было показано в одном из экспериментов, картинок, и затем с точностью не менее 95% их узнавать в потоке новых и старых картинок. То есть это стимулы, на которые ограничений по объему запоминания практически нет. Их очень удобно использовать в таких экспериментах. И, собственно, сами эксперименты, один из экспериментов, который показал Джереми, заключается в следующем. Вам нужно сначала запомнить набор объектов, которых набор может состоять из 1 и до 16 объектов, а затем в наборе для зрительного поиска, который также может состоять из разного количества таких элементов, вам нужно найти объект, который был в наборе запоминания, и сказать, был ли он или нет. И если построить затем график, на котором отобразить время реакции в зависимости от размера зрительного множества, то график будет иметь, в общем-то, линейную форму, то есть чем больше объектов на экране, тем, соответственно, пропорционально этому возрастает время реакции, и это такая хорошая линейная функция. Если те же самые данные, как показано на этом графике, отобразить так, чтобы на оси абсцисс был объем набора для запоминания, то вы увидите, что эта функция хоть и возрастающая, но нелинейная, да, она вот такая искривленная.
So, is this curve interesting? It could be boring. Here's why it could be boring. In lots of reaction time studies, certainly lots of visual search experiments, you sometimes get a curve like this that is just a speed accuracy trade-off. That means that you get faster, say here, but you also make more mistakes. And to test that, we replicated the basic experiment, and we did a slightly different version. What we did, instead of having people say yes, no, what we did was we said, there's always one of your targets there. Put the mouse over it and click it. And that reduces error rates. It makes speed accuracy trade-offs much smaller, and click. And the data look basically the same. This is from a second experiment, looks just like the first experiment. Linear functions for target present, for the visual set size effect, curved functions for the memory set size. Okay, so it's probably a real curve. What kind of curve is it? Well, if we transform this axis to a log axis, if we scale these logarithmically, all of a sudden these are really linear functions on a log scale. So this is log 2 of the memory set size, right? 2, 4, 8, 16 items. And you get this very, very linear sort of look. So the suggestion is that what saves you from the Facebook disaster is that you're not multiplying linear visual set size by linear memory set size. You're multiplying visual set size times the log of the memory set size. And no, I didn't put an answer in there. That, for the Facebook example I gave, that takes the time required from 45 minutes to something more like 30 seconds, which is a much more reasonable assumption for the task. Did you want to do it?
Oh, okay.
Okay.
Вот та отклоняющаяся от прямой функция, которую Джереми получил для функция зависимости времени реакции от объема множества для запоминания, вообще могла бы выглядеть тривиальной, потому что в литературе по времени реакции известен феномен так называемого компромисса между точностью и скоростью. Когда от вас требуется скоростной ответ, то вы начинаете просто давать ответы быстро, тем самым повышая количество ошибок, и таким образом время реакции действительно уменьшается, но тем самым не достигается полная переработка всех элементов. И чтобы это проверить, был проведен эксперимент, в котором испытуемых просили не просто обнаруживать элемент, который они запомнили, а просили его локализовывать, то есть показывать, кликать на то место, где он расположен. Обычно это очень сильно снижает количество ошибок, что и произошло в эксперименте. Таким образом уничтожает вот этот компромисс точности и скорости. Но несмотря на это, в результате получилось, что функции имеют точно такую же криволинейную форму. И вопрос, собственно, в том, что же это за такая криволинейная функция. Судя по всему, она приближается больше всего к логарифму. И, соответственно, если мы сделаем так называемое лог-линейное преобразование, то есть вместо линейного масштаба мы просто выберем единицы логарифмические, то функция преобразуется тоже в хорошую такую линейную, и, похоже, это спасает нас вот от этой фейсбучной катастрофы. То есть, на самом деле, скорость вашего поиска пропорциональна не количеству объектов, которые хранятся у вас в памяти, а логарифму этих объектов. Тем самым поиск на самом деле гораздо быстрее, и он ускоряется по мере того, как растет количество элементов, которые вы должны запомнить.
So that's just a memory set size of up to 16. I said you can do lots of objects, so let's do 100. So again, we're just showing people objects one after the other. They're not practicing, they're not going home and rehearsing for days and days. And they get 93% correct when we test their memory on it. And here's what the data look like. These are the functions you saw before. Here's the data for 100. It's more difficult. Again, it's slower. You have to search through a memory set of 100, but it's not that bad. It's kind of fun, actually. Well, I don't know. Maybe I have a weird idea of fun. But, well, if you memorize 100 objects, if I say, tell me the 100 objects you know, you say, I have no idea. Right? I remember a couple of them. But then I put 16 objects on the screen, I say, find the one that you've seen that's part of your memory set. No problem. Oh, data that I'm not going to show you. This is, how many people here are memory researchers? 2, okay, great. I'll tell them anyway. You might think this is just familiarity. But if you balance the frequency with which distractor items that are not in your set and target items that are in your set, if you balance the frequencies of those, you get exactly the same data. It's not a familiarity effect if you're a memory researcher. Because all my memory researcher friends are always saying, we know about that, it's just a familiarity effect. It's not. Okay, anyway, okay, that's the absent trials. Okay, so what happens with this memory function? I claim this is a log function of the memory set size. Here's the data I showed you before. I can do a linear regression on the log memory set size. I can do a linear regression through that. And I can extrapolate out here to where the data should be for set size 100. Right? I can use these data to predict set size 100 if it's really a log scale. And here's what that looks like. Here are the data points. The lines are predicted from here. They are right on top of it. And it's beautiful, you should think. Because this is one set of subjects. This is a different set of subjects. This is really a logarithmic function. It's not just any old curved function, whatever Rich Schifrin says. When I gave this talk for Rich Schifrin, he said, oh, we always get curved functions. He says, this is a log function, not just a curved function. Was that? Yep, okay.
Соответственно, перед этим эксперименты описывались для тех случаев, когда, в общем-то, запоминать элементов нужно было не так много, всего до 16. Коллеги, Джереми и его коллеги попробовали проверить, а что будет, если увеличить объем запоминаемого множества до, возможно, сотен объектов. И опять вы не испытаете никаких особых трудностей с их запоминанием и затем узнаванием в наборе для зрительного поиска. И, соответственно, основная идея была проверить, будет ли сохраняться эта логарифмическая зависимость. И это были уже новые испытуемые, были созданы новые наборы. И тем не менее, опираясь на данные первых экспериментов и предполагая, что функция вот эта вот имеет такую логарифмическую форму, да, или лог-линейную форму, как показано здесь, можно экстраполировать данные с, допустим, 16 объектов в памяти на сотни объектов в памяти. То есть, когда логарифм мы увеличиваем допустим, с 4 до 6, в разы подскакивает количество запоминаемых объектов, но предсказание, значит, у нас такое, что они попадут все равно на эти продолжающиеся линии. И что было получено в экспериментах, и что просто замечательно и поразительно, это то, что с новыми стимулами, на новых испытуемых эти точки легли на вот эти вот прямые, то есть абсолютно соответствует предсказаниям, и действительно это логарифмическая функция для памяти.
So, when do we get these sort of log functions? They show up elsewhere in experimental psychology. This is some data on different kind of memory search, a long-term memory search from Burroughs and Okada back in the 70s. There is something known as Hicks law or the Hicks-Hyman law. If you are doing multiple choice reaction times, so you have, if you have a 1 or a 2 shows up on the screen. If it's a 1, you push the 1 button. If it's a 2, you push the 2 button. Okay, now we have a 1 through an 8. If it's the 1, you push the 1 button, 2, 2, 3, 3, so on. It will take you longer when there are 8 items than when there are 2, and that function is also logarithmic. That's known as Hicks law. So these functions show up elsewhere in psychology. How general is this in hybrid search? Let's do a different experiment. Here's a different version of the experiment. What I'm going to do, what you are going to do here, is on each trial, there will be one item that you have not seen before. So now, rather than asking you to tell me, was this item in your memory set, I am asking, was this item not in your memory set? And I'm going to build the memory set on every trial. So now you have a memory set size of 1, right? Okay, tell me the name of the new item. Okay, not that hard with 2. But now you have a memory set size of 2, okay? Yeah, it doesn't really matter, but you know absolutely which one is new, right? Now you have a memory set size of 3. Yeah. You can feel yourself adding to the memory set each time. You're not having any real trouble doing the task, right? It's quite easy. Keys, yeah, I think that. Oh, no, there's another one. I don't know what he is. Knives up there. Right, so it's obviously possible to do that task. I'm increasing the memory set on every trial. And we don't increase the visual set size on every trial. Initially, the way you were seeing it, you would increase because you have to. Once we got to 12 items, every visual display either had 6 or 12 items in it. But we kept going. We really kept going. We went out to 500 items. No practice, no rehearsal. You're entering one into memory on each trial. And the data look like this. Again, you get these lovely curved functions. These are now averaged over bins of, I think, 50 trials. I don't quite remember. But you see, you get the curved reaction time. If we plot this not on the memory set size, but on log memory, you can see that it's very nice and linear until you get out to about 500. Here, you really do get a speed accuracy trade-off. Once you get to 500, people start making mistakes. If we compare those data to the previous data, so here's the new data. This is the data I showed you. These are the data I showed you before. It looks a little different. You can see that that the tell me the new object task is a little harder. But if we equate the intercepts of these functions, if we line them up on their intercepts, you see that the progression of memory set sizes is very smooth, right? This is from one experiment, this is set size 2, set size 4, that's set size 6 from the other experiment, set size 8, set size 16, set size 12 from the new experiment, set size 16. So it makes a very, if we plot the slope of those functions, it's a very smooth, continuous function. What's not smooth are the intercepts. The task is much more, the decision. Intercepts in visual search experiments reflect decision processes usually. How long does it take you to decide that the thing you have found really is the target? And the decision in that new task is harder. But the basic memory, log linear memory function is the same.
Собственно говоря, такие подобные логарифмические зависимости уже были известны, в частности, в более ранних исследованиях поисков памяти и в исследованиях, которые привели к формулировке закона Хика-Хаймана о зависимости времени реакции от количества альтернатив. Она тоже логарифмическая. Но Джереми и коллеги решили проверить, насколько общим является вот этот логарифмический эффект в задаче с поиском не старого, то есть до этого запомненного объекта, а объекта нового, который в памяти еще, у нас есть информация в памяти, что его еще не было. Демонстрации, которые Джереми показал, вам предлагалось запоминать объекты, которые уже были предъявлены, и называть те объекты, которые вы видите в первый раз. В реальном эксперименте, который состоял из многих проб, количество объектов на экране, то есть зрительный набор, был либо 6, либо 12, но по мере движения по эксперименту, да, то есть накопления проб, каждый раз появлялся все новый и новый объект для памяти, и таким образом за весь эксперимент их количество достигало примерно 600. И, соответственно, строилась функция зависимости времени реакции от набора. И оказалось, что, опять же, существует некоторая разница в угле наклона для зрительного набора в зависимости от его объема. То есть для 6 и для 12 он был немножко разный. И при этом сохранялась, в принципе, лог-линейная зависимость от количества элементов в памяти. И, казалось бы, сами эти функции, если их сопоставить с данными прошлого эксперимента, где нужно было опознавать старые объекты, эти функции выше, поскольку задачи разные, но если те функции сдвинуть вниз, совместив начало функции с началом функции в двух предыдущих экспериментах, то оказывается, что они очень похожи, то есть что для задачи с новым объектом, что для задачи со старым объектом зависимость одна и та же, и даже абсолютные величины наклонов примерно одинаковые. Разница только вот в этой самой константе, которая связывается, возможно, с принятием решения, которое, наверное, в случае задачи с новым объектом, это решение просто более сложное.
So now let's try making a little model of this, and we can start with a basic model that says, okay, there's a serial visual search, one item after another, that is interlaced with a log memory search. I select an item, I do log memory. If that's not my target, I go back, I do visual search again. That's a nice start, it's not right. Let's modify that a little. Let's start with this part, and I can show you that it's not just a simple one after the other serial search. the way to show that is, okay, memorize these guys. Oh, also notice that you have no problem doing a new set of 4. The ones from the previous demos are actually probably still in your memory somewhere, but they don't interfere. You can switch back and forth between sets that are held in your memory, it turns out. But anyway, you remember these 4, right? Okay? So say yes or no if one of your targets is present here. Ready?
Yes.
Yes.
Okay, very easy. And the relevant point here is that you didn't search these guys at all, right? They just were not candidate targets. So we don't want, if you were paying attention yesterday, you don't want to call the visual part a serial visual search. You want to say it's a guided visual search. There are some things that might be your members of your memory set, and you pay attention to them. Now, we can work a little more on this. Here's a new set to memorize. You will notice that they have a certain categorical nature to this particular set. Right? Paid attention to everybody now. Okay, tell me, oh, I guess this time clap if one is present. Took a little while, but okay, which one is it?
Seal.
The seal down the bottom. Everybody knows that you weren't just guessing, or the people who found it weren't just guessing. Okay, here we can just refresh your memory set, because I want to do another example. Again, clap if one of them is your target. So I will assert that that was faster. Of course, it's not one of the world's great data points, but I will. If we do this in the lab, we have done this in the lab. I will show you the data. If we do this in the lab, we can show that that this version would be faster. Why is it faster? Well, some of it is faster because of the guided search part. You didn't bother to pay any attention to a pointy triangle, whatever it was, because it was never going to be one of those animals. So you guided your attention away from it. But there's a second thing that helps you here. You probably did, some of you probably did pay attention to items like this. But when you attended to that, you very rapidly identified the object. And then you could ask the question, is that object possibly in my memory set? And if I identify, I don't know quite what this is, I think it's a scrub brush of some sort, but it's not an animal, right? If I look at this, I identify it as not an animal, I just go straight back up here and select something else. I don't need to do the memory search. I only do the memory search if I select something. It's identified in that greenish box as an animal. Then I have to go down to do this logarithmic search and say, no, that wasn't one of my animals, go back through this, or, you know, poof. Ah, yes, I'm done. Oh, this says massively parallel search. It should say massively parallel search through memory. When you are identifying an object, you can think of that as a search through memory. Here's the visual stimulus. What object is that? That must be parallelized in some fashion. We don't really know how. Okay, we'll test this model in a second, but maybe we should talk about it first in Russian.
Окей. Собственно говоря, предлагается построить для начала небольшую модельку. В самом простом виде, да, у нас есть последовательный и неэффективный зрительный поиск. Неэффективный значит, что каждый следующий объект влечет за собой прибавку во времени реакции. И с другой стороны есть вот этот логарифмический поиск в памяти, они каким-то образом между собой связаны. Но действительно это работает именно таким образом. И в первой демонстрации, когда вам нужно было искать, вам нужно было запомнить объекты для поиска, а затем искать их среди других объектов, реалистичных, да, натуралистичных объектов и букв, вы нашли очень быстро, потому что буквы вы не рассматривали вообще. И это значит, что тут Джереми напоминает про вчерашнюю лекцию, про так называемый механизм управляемого поиска. Если есть стимулы, которые вообще никак не похожи на вашу цель, не обладают никакими признаками, вы их тут же отвергаете, даже не смотря, и, соответственно, поиск становится на самом деле более эффективным, и это зрительное управление вниманием. С другой стороны, что касается поиска в памяти, возможно, во втором примере, когда все цели, которые были предложены для поиска, относятся к категории животных, то вы можете с помощью зрительного механизма управления вниманием отвергнуть какие-то объекты, которые точно не обладают признаками вашей цели. Например, чемоданчик, поскольку он состоит из прямых линий и углов, никак не может быть животным. То есть вы на зрительной основе их отбрасываете. На какие-то объекты вы обращаете внимание, потому что они в принципе зрительно похожи на животных, но зато вы их отвергаете на стадии поиска в памяти, потому что память вам подсказывает, что они точно не могут быть животными. Как, например, эти боксерские перчатки, вот эта вот штука, которую ни Джереми, ни я не поняли, что это такое. И, наконец, это происходит тоже очень быстро. И тогда вы можете переключиться на поиск снова. И, наконец, когда вы находите объекты, которые, возможно, являются животными, то начинается логарифмический поиск в памяти уже среди тех объектов, которые вы действительно запоминали. И, кстати говоря, вам очень легко переключаться между списками разных объектов, которые вы запоминали до этого и которые вам нужно запоминать сейчас.
Okay, so let's test this model. Here's how we'll do it. I'm not going to actually run the demo on you this time. You've sort of seen it. We'll get people to memorize 2, 4, 8, or 16 animals, arbitrary animals. And in the first version of the experiment, we will show them visual displays that have a variable number of animals in them and a variable number of objects that we decided come from categories that are kind of like animal shapes. Right? They don't look exactly like animals, but, you know, I don't know, you might have to pay attention to that to decide it was not, I don't know what it might be, an octopus or something. A very strange octopus. What we'll plot here is the slope of the visual set size function as a function of the memory set size, and that gives you the cost of each additional item. Okay, so for the animals, so the animals where you have to do the memory set size, you get the usual, a different version of, but it's basically the same log function. If you search for things that might be animals but are not animals, you get this function. It's basically flat. It's not at 0. It suggests that people were attending to some of those objects, but then saying that's not an animal, it can't be in my target set. So this is the additional cost of having to do the memory set search. If it's a real animal, you have to do the memory search. If it's not a real animal, you stop after you identify it as gloves or something like that. Second version, we will do, again, memorize some animals, but now we'll do animals among things that are never going to be animals. These are things you should guide away from, right? Square things, circular things that just are not animals. And there you see that those items incur no cost at all. They're right down there at 0 because the observer simply never attended to it at all. You could have all the coins you wanted in the display, and it wouldn't change the reaction time. So so you end up with this model of 3 processes that work together. You select an item that might be a target. You decide if it can be in the target set. If it can be in the target set, you do a logarithmic memory search, and then you loop back. We'll explain. So the one thing we haven't explained is how you're going to get this logarithmic function. So I'll try to do that next.
Итак, Джереми рассказывал про 2 эксперимента, в которых модель, которую он предложил, проверяется. В одном из экспериментов испытуемые должны были запомнить набор объектов, целей, которые все относились к категории животных, и искать среди других объектов других категорий или других животных, которые им не нужно было запоминать, но которые в принципе были более-менее похожи так или иначе на животных. И было обнаружено, что поиск среди цели среди дистракторов, которыми являются другие животные той же категории, крайне неэффективен, и более того, он становится все более и более неэффективным, то есть возрастает вот крутизна этого наклона функции зрительного поиска, как функция от количества объектов, по мере увеличения количества объектов для запоминания. В то время как поиск среди дистракторов, которые животными не являются, он в принципе был не очень эффективным, то есть вот это вот время реакции все-таки серьезно зависело от количества объектов на экране, но не возрастал никаким образом этот наклон. И во втором эксперименте поиск осуществлялся среди дистракторов, которые не только категориально не похожи на целевой объект, но и по своим зрительным признакам тоже никак на них не похожи. Рамки, монетки не обладают ничем похожим на животное, и такой поиск был эффективным, то есть наклон всегда был около нуля. То есть это значит, что сколько бы объектов не показывалось зрительно, и сколько бы объектов испытуемый не запоминал, не удерживал в памяти, время реакции оставалось примерно одним и тем же.
Okay, so the part that we haven't explained yet, or haven't modeled yet, is where does this log function come from? My first question before launching into this model is, how many people here are familiar with diffusion models of decisions? Does this? No, okay, a couple. Okay, let's say something about this. The originator, well, there are different versions, but Roger Ratcliffe in the US is the leading name for these kinds of models. The basic question is, how do you decide that this is Katja? And the answer is, well, the style of modeling is, you start collecting information, in this case, maybe sensory information, and it proceeds, there's noise, it proceeds as a sort of a random walk, and you have some threshold up there that is the Katja threshold in this particular case. When you get there, you say, yes, that's her. That's the way these models are constructed. The slope of this function is how rapidly the information is accumulating. The point at which it hits the boundary is the reaction time. These sort of models do a wonderful job modeling reaction time distributions for a wide range of perceptual and cognitive tasks. You can find evidence for accumulation in neural signals. It's a nice, robust kind of a model. Maybe we want to, why don't you give the basic diffusion model story, and then we'll go on.
Собственно, объяснение, которое Джереми для начала пытался искать вот такой зависимости времени реакции от набора зрительного и набора в памяти основывается на диффузионной модели, которая эксплуатирует идею случайного блуждания как механизма накопления информации или накопления свидетельств о том, что данный стимул принадлежит, например, данной категории. И, соответственно, время реакции в этой модели – это функция от того времени, которое требуется для накопления информации и достижения некоего порога решения, то есть когда количество свидетельств, накопленных за это время, оказывается достаточным для того, чтобы определить, например, что Катя – это Катя. Okay.
Oh, that was great. Okay. Well, all right. Let's suppose now that I pay attention to this fine gentleman in the front row, and I ask, "Is this Katya?" I will also accumulate evidence, but it won't go anywhere. We hope. Just a random walk, going nowhere, and I will not declare that he is Katya, unless I set the boundary too low. If I set the boundary, if I make too liberal a criterion would be another way of stating it. If I set the boundary too low, the random walk might bump into the boundary by mistake, and I would say, oh my God, that's Katya. She grew a beard. Which is weird, but that's okay. Okay, anyway. When we apply this to memory search, the idea is more something like this. I look back I'm paying attention to Katya. I'm trying to decide. I have two people I know here. One is Katya, one is Igor. Who is this? So I have two people in my memory set in this case. And Katya evidence accumulates to a positive decision. And as long as I didn't do something stupid with the boundary, the information accumulated about is that Igor says, no, that's not Igor, that's Katya. So the idea is that for every item in your memory set, you launch another diffuser. So if you've got 16 items in memory, there are 16 of these things going on. And you can imagine that the more items that are sitting in memory, and the more diffusers that are going on, the greater the chance that just by chance, just by the noise, somebody will bump into the decision boundary and you will make a false alarm error. And you don't want to do that. The way to prevent that is, as you have more and more items that you are searching in memory, you should push this boundary higher and higher. Remember that the higher the boundary, the longer it will take to hit that threshold. And so the reaction time will get longer. So this predicts that if you hold errors roughly constant, that the reaction time will increase as you increase the number of items in the memory set. That's nice. But what does that function look like? Oh, I didn't put that in the middle there. Well, that's too bad. We're going to take a quick... No, we're not. You can look at the functions down here. So Ratcliffe, he's the diffusion guy. Lighty is one of his students. The data underneath here that I put this on top of for some reason, this is me doing Monte Carlo simulation of this kind of model. This is Lighty and Ratcliffe doing the math. I can't do the math, but I can tell my MATLAB code, you know. Pretend this is what's happening. Okay, oh, look at that. What you get, so this is simulated reaction time. This is log of the simulated memory set size. And you can see that you get nice straight line functions. This kind of model predicts specifically logarithmic functions under quite general versions of diffusion models. You can play this. This is all arbitrary playing with the parameters. You can fiddle around with the parameters of your model. It doesn't change the basic result, which is if you keep the error rate roughly constant, the increase in reaction time as the memory set size increases will be basically logarithmic. Yeah, the math also does the same thing, which is nice. Yeah.
Итак, каким образом вот эта вот диффузионная модель позволяет объяснить логарифмический поиск в памяти? Дело в том, что всякий раз, когда у нас появляется какая-то новая альтернатива, по которой возможны свидетельства, да, накопление свидетельств, например, в памяти у Джереми хранится образ Кати и образ Игоря. Вот Катя, вот Игорь. И Джереми надо решить, допустим, что это Катя. Начинается сбор свидетельств, а представление о том, что в памяти есть Игорь, создает некий новый процесс, который, в общем-то, является шумовым процессом. И если критерий принятия решения о том, что Катя это Катя, установлен слишком низко, то есть он очень либеральный, по минимуму признаков Катя будет категоризована как Катя, или не Катя вовсе, соответственно, есть большая вероятность того, что накопление свидетельств в пользу другой гипотезы, например, о том, что это Игорь, в какой-то момент ударится об этот порог, и тогда будет принято ложное решение, ложная тревога, и будет ложное опознание. Чем больше таких процессов, то есть, например, чем больше элементов в памяти мы храним, тем, соответственно, больше шума, и тем больше вероятности, что в какой-то момент один из этих процессов накопления информации случайно ударит соответствующий порог, и будет ложная тревога. И чем больше элементов, тем выше устанавливается порог принятия решения, соответственно, тем больше времени нужно для накопления информации. То есть это объясняет, почему время реакции, если мы желаем сохранить неизменным уровень ошибок, соответственно, почему время реакции увеличивается. Если этот процесс случайного блуждания попытаться промоделировать математически, что, собственно говоря, Джереми делал в сотрудничестве с Редклиффом, одним из основных идеологов этих моделей диффузионных. Собственно, математическая симуляция Монте-Карло приводит к тому, что действительно точки ложатся на лог-линейную функцию, и таким образом, в общем-то, очень хорошо все это соответствует модели логарифмического поиска в памяти.
So, I'm happy with this. This is a pretty good model. But you might complain that all of the experiments that I showed you have to do with searching for specific images of specific objects. You know, this bottle in this position, not bottles in general. And most of the time you don't do that, right? Most of the time you say, well, if we go back to the initial example, when your mother sends you to the buffet to get a shrimp, she doesn't say, I want this exact shrimp, right? It looked, you know, she said, get me a shrimp, get me a banana, or you know, you go to the woods and you say, are there any birds here, or something, something like that. So, does this work if you're not using highly precise templates of items in your memory? Here's a version where you're looking for categories. You can't go and memorize, it's much more difficult, it turns out, to memorize 100 categories. It's hard to even define 100 categories and raid the internet for pictures of 100 categories. But you can do 20 without too much trouble. I won't do 20 with you. I'll just say, clap if you see a fruit or an animal. So that would just be a memory set size of 2. Yeah, okay, that's easy. Okay, ready? No fruits or animals there. How about here? Yeah, so easy task to do, and the important point is the data look the same again. This is memory set size, reaction time, log curved kinds of functions. They are different than the data I showed you before, but they are different in that they are, it's a harder task. If you are, well, it's easier to see here with just 2 of them. If you're looking for one of 16 objects, it's much faster than if you're looking for one of 16 categories. But you can see that this is basically an additive difference. That's just telling you that the decision process, what's changing is the decision process, not the search process. So you can search through a memory set of categories perfectly easily.
Вопрос, однако, в том, насколько вот все эти закономерности, связанные с гибридным поиском объектов, специфических, да, объектов, которые имеют определенный вид, может быть распространено на какие-то менее точные представления. Собственно говоря, наши задачи поиска в памяти, они именно такие. Мы не ищем что-то совершенно специфическое, да, не какую-то конкретную креветку или не какой-то конкретный банан. В принципе, объект может принимать много разных форм и вообще может описываться очень такой широкой категорией, очень расплывчатой. Будет ли это работать в гибридном поиске? И в эксперименте, в демонстрации, которую вам показывал Джереми, вы должны были искать не конкретные объекты, которые вы должны были запомнить, а какие-то довольно общие, в общем виде названные категории, типа фруктов, что там еще было, не помню. Да, и животных. И оказывается, что функция, в общем-то, имеет такой вид, хотя, конечно, задача поиска по категориям более сложная, и в целом вы находите объекты быстрее всегда, чем находите категории, но логарифмическая зависимость сохраняется, и даже наклон этой функции очень похож, как вы видите на рисунке. Разница только в абсолютной вот этой прибавке, да, а так, в принципе, эффект аддитивный, и эффект получается довольно общим, работает даже на обширных категориях.
So one last experiment for the language people here. Let's do this with words. In particular, what we didn't get people to memorize random lists of words. We said, tell us a phrase that you absolutely know by heart. Right? And Igor says this is not a good one in Russia, but this is from a children's song about London Bridge is falling down. So I don't know, Moscow Bridge is falling down or something. Uh-oh. LCD projector is falling down. Yeah, that's a different song. Anyway, we got them to give us different phrases of different lengths, and we used their specific phrases as the stimuli. We were interested in a couple of things. One of them was whether or not you would get serial position effects. If you do London Bridge is falling down, are you faster to find London? Actually, this is what we've been trying to break hybrid search. When does it not work? We thought this is sure to be something different, because what will happen is London will be faster than that down, and there will be a systematic serial position effect. And the experiment would look like this. So if you find one of the words in London Bridge is falling down, say which one you find.
Falling.
Good. Okay, you want to do it again?
London.
London, excellent. You can try this in Russian, but we were going to change it. Igor and I were trying to change it, but it turns out I have no Cyrillic font on this computer, sadly. But in any case, again, you get basically this logarithmic function. I didn't put the data in, but there is no evidence of a serial position function, and there is no evidence that important words are any faster than unimportant words. In this task, as in every other memory and visual, hybrid visual search task that we have done, we get the same, basically the same results. It always ends up looking the same.
Ну и последний эксперимент, о котором хотел сказать Джереми, со словами. Вам предложено было запомнить фразу. Как правило, использовались в эксперименте фразы, которые люди хорошо знают наизусть. И эта фраза могли быть разной длины, соответственно, что задавало разный объем множества для поиска в памяти. И затем надо было искать и называть слова из этой фразы, если они были на экране. Отдельно проверялся так называемый позиционный эффект памяти, согласно которому вы должны были бы быстрее всего реагировать на слова, которые были в начале и в конце фразы. И, соответственно, если варьировать объем для запоминания и множество для запоминания, объем множества для зрительного поиска, то в результате мы получаем опять вот такую вот искривленную функцию, которая, может быть, не так хорошо соответствует логарифмически, как предыдущие зрительные данные, но, тем не менее, она гораздо ближе по своей форме к логарифмической, чем к линейной.
So just to summarize, if you were looking to see if any of your professors are in this particular group, you've got a big visual set size, you've got a set of professors held in memory. You will do a guided visual selection. You'll select people. You will not check whether the water bottle is one of your professors because it's just the wrong visual stimulus altogether. Having selected something that might be a professor, you identify it at least categorically. So, much too young to be professor, go back and select something else. If it's a candidate, possibly as one of your professors, you now do a search through the set of your professors. If it's a different professor, not for yours, you go back and search again. If it's your professor, you win. And this, we think, or you lose. What we think is happening here is that if you have, I don't know, 5 professors this week, 5 diffusers get launched, you put a boundary someplace that will prevent you from having too many false alarm errors, and that will determine how long that logarithmic memory search will take. And I should say that if you liked this lecture more than yesterday's lecture, you probably should really go into experimental psych or cognitive psych. Right? This was the nerd lecture. What's the word for nerd? Okay, anyway, the word is Igor, but don't tell him.
You told it.
But this is a much more technical talk, obviously, than yesterday. But you should explain the summary if you like. But thank you.
Okay. Собственно, это было резюме модели. Итак, если вы выполняете реальную задачу зрительного поиска, когда, допустим, вы ищете по аудитории своего профессора, то работает сразу несколько процессов. В первую очередь, это управляемая зрительная селекция, когда вы отбираете те объекты, которые, возможно, похожи на вашу цель по признакам, и вряд ли вы будете искать среди бутылок воды а вы будете все-таки смотреть на объекты, которые похожи на людей. Затем будете осуществлять более специфический поиск, для чего обратитесь к своей памяти и поймете, что, скажем, люди, которые слишком молоды, вряд ли могут быть вашим профессором. Это еще сузит круг ваших поисков. А среди оставшихся объектов вы запустите логарифмический поиск памяти и, возможно, достигнете успеха, возможно, не достигнете. Ну и финальное замечание. Если вам понравилась эта лекция больше, чем вчерашняя, хотя она была, как Джереми сказал, для ботаников, то, возможно, вы хорошо чувствуете и вас ждет успех в области когнитивной науки. На этом спасибо.
Okay.
Now we have time for questions.
Yeah. Yes, Russian or English, take your pick.
Sorry, you cannot stand up. That's no space here.
Okay, I'll stand up. There's space here.
Could you tell us about the architecture of the box 3? I mean, in Radcliffe model, you have a separate graph for each, say, recognizer. And if the model, the output of the model is guided by logarithmic law, not a linear law, it means that recognizer shares some resources or some procedures. What do they share?
Yeah, so I think I would have to claim that if you imagine that you have 10 things in memory, so you have 10 different separate processes running to 10 different boundaries, that the setting of the boundary is somehow yoked. That you raise all the boundaries proportionally. I think that will work. When I modeled it, I just had a single bound and 10 identical diffusers, but I don't think it's in principle different as long as the bounds are yoked. Though I would recommend the Lighty and Ratcliffe paper for probably a more precise answer to that question.
Other questions?
Yeah.
I had a question about your syntax example. So you said that people who would say London Bridge is falling down would recognize London out of a spread faster than they would recognize down.
Well, that's what I thought. That turns out not to be true.
Oh, that's what I was thinking. Never mind.
Oh, okay. No, it seemed, and it particularly seemed true for, we asked people to give us the longest passage that they knew by heart, that they thought they could reliably give us by heart. And so in the US, that tends to be the United States Pledge of Allegiance, or sometimes it's a psalm from the Bible or something like that, but many dozens of words. And we were sure that you would locate a word and sort of start at the beginning. And you know, I pledge allegiance to the flag, anyway. But no, it's independent of order in the phrase.
So do you find that it doesn't conform to phrase structure rules? Because mentally a lot of...
No, well, we didn't look at phrase structure rules.
Sure.
We don't even get just straight out primacy, right? You know, the most basic is the first word better.
Yeah.
But now look, I suspect that if you did a more subtle version of this, there must be linguistic effects that you could tease out of it. But the main effect is that memory search looks like all the other memory searches I showed you. It's just another loggy search.
But did you try to make search of whole phrase among other phrases?
Oh, no, that's interesting. I suspect that would run that you would search until you found the first unique word. Right? You know, I probably wouldn't do it, but as soon as I got in the US to pledge, okay, that sounds like, oh, and plus, with big long phrases, it's going to be very messy on the screen.
Yeah, maybe not so big because.
Yeah. No, but we only did this with single words. And you might also imagine that you would start to get with words some kinds of guiding effects with word shape and things like that. But again, we didn't look for anything quite that subtle.
Игорь, пожалуйста, спроси, у меня один вопрос на понимание, а другой такой более sophisticated. На понимание, правильно я понимаю, что та аддитивная константа, разница интерсептов по всем точкам, это и есть вклад в процесс принятия решения в конечную эффективность зрительного поиска?
I hope he was saying that was sophisticated and not that it wasn't sophisticated.
Yeah. The first is just for understanding. Is that right that the difference between the intercepts of different levels, for example, object search or categorical search, is ascribed to the difference in decision process?
Yeah, I think so. I think that if I want to know, is this object a specific animal, that's a shorter diffusion process than if I want to say, is it any animal. But I don't know that. It's just a guess.
Хорошо, аккумуляторная модель соответствует. И второй вопрос, уже как психофизик психофизику. Правильно я понимаю, или неправильно я понимаю, что это более, если корректно говорить, это метафора логарифмической функции, или конкретная работа по goodness of fit проводилась, нудная, конкретная, вместе с математиками, и доказана логарифмическая функция.
So it is about the psychophysics aspect of this work. Is the finding that the function is logarithmic just a kind of metaphor, or it is strict work with mathematicians and testing for goodness of fit and so on?
Oh, so log functions are a very good fit. There are other curvilinear functions that would also be a good fit, quite a good fit. I think that the experiment where we predicted the data for set size 100 from the small set sizes, the fact that that fits so well is an argument that this really is logarithmic. I think that if you came along tomorrow and said, I know that this is not exactly logarithmic, it's actually, Hoosiismic, whatever, some weird function I've never heard of, that's okay. I would adapt. I would have to think how to adapt the modeling. What's important is that the shape of those functions is constraining models, that it's such a consistent result. You can certainly tell that it's not linear. It's probably logarithmic, and that's telling you something important about how the brain is doing these sorts of tasks. Would I want to give you my first child, who is a graduate student in psychology, if it turns out that it's not logarithmic? No. But I think it's logarithmic.
Thanks a lot.
May I ask you, it was just beautiful to show us, let's say, these memory sites and in so-called, let's say, static pictures, like choose, is it there between the butterflies, another animal, whatever. However, I would like to ask you, do you expect the same curves in a dynamic process, like, let's say, a motor learning, because you need a lot of steps, a lot of items which are just connecting each other, which is just compose the whole picture, like I'm doing, let's say, the high jump, and there are a lot of crucial processes just to see, because it's really important, let's say, in a way of explicit motor learning, that I'm observing and I'm giving, or I'm getting a commands as well.
So I could imagine that, that in the early stages of that kind of learning, that there might well be this kind of memory search going on. But after that, I bet we are in the automaticity literature. And I don't want to say anything about the automaticity literature. I think probably you would end up with sequence, a sequence so that this action would now tell you the next action, and it would be a memory set size of 1 at that point. But initially, so I think that the memory sets, the memory search aspect of this explains why I can't dance. Because they told me, well, there are many reasons I can't dance, but one of them is they tell me 6 different things, and my search through my motor memory is so slow that by the time I remember I'm supposed to go like this, she's gone somewhere else completely. So I married the woman who promised we would not have to dance at the wedding. Is this an answer?
Yeah, in some way, yeah.
Yeah.
Any other questions?
Anything else?
I think no other questions. Okay,
Thank you.
Thank you, Jeremy.
Come visit when you're in Boston.
Everyone is going to Boston right now.
Yeah, well, there are empty seats on the flight tomorrow. Put a whole pile of people in there. Okay, thank you.
Thank you.